Good evening, everyone. We are in the week 4 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 4 is about variable frequency control methods. I am Teja Golla, a 5th year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. So let me share my screen. Can you see my screen?
Yes, sir. I can see your screen.
Okay. So let us start with some basic introduction to the architecture of variable frequency control methods, and then we'll also solve a few problems subsequent to this. And so can you identify which control this is? Looking at this figure, which control?
Constant on time.
Okay, yes, very good. So this is constant on time, and constant on time can be voltage based as well as current based. So can you identify whether it is voltage based control or current based control?
Voltage based control.
Voltage based, yes. So this is voltage based constant on time control. So we'll just browse through some important aspects of this, and like how or why constant on time or variable frequency in general are needed when we have fixed frequency. So how they can be beneficial and why sometimes they are beneficial. And also we'll solve few problems subsequently. So to start with, this is voltage based. Constant on time. It is also called as COFT, where C stands for constant and O stands for on, T stands for time. So COFT control, constant on time control. So the other name is COFT, constant on time control. So why it is voltage based? Because we can see it is only single loop. First of all, there is voltage loop and there is a comparator followed by some block and then monoshot timer, and it is generating gate pulse. So can anyone identify the name of this block that I'm showing over here? What is the name of this block?
Rising edge
Yes.
detector.
So yes, rising edge detector or edge detection circuit. So in MATLAB, you'll find this edge detection circuit. So what happens is basically we have a comparator, and then the input is the reference as well as the V0. So the plus and minus sign are very crucial. We have plus for Vref and minus for V0. So whenever V0 is below Vref, then it will become 1. Whenever V0 is above Vref, then it will become 0. So when will we see a rising edge? When V0 is going below Vref or V0 is going above Vref? So when can we see a rising edge? When V0 goes below Vref or when V0 goes above Vref, sorry.
When V0 is below Vref.
Yes. So whenever V0 is going below Vref, then there will be a rising edge. So as also shown over here. So basically QC is 1. So QC is equals to 1 if V0 is less than Vref, and 0 if V0 is greater than Vref. So what happens here is, so whenever V0 is going below Vref, it means that our output voltage has gone lesser than the required reference voltage. So what we need to do, we need to charge it, right? So we need to push the power, or we need to charge the output capacitance. So basically we need to turn on the switch. So that's why whenever V0 is going below Vref, we'll see a rising edge. So when this rising edge is triggered, so now this will trigger a signal, right? It will be basically a, so if we draw the waveform, it will be, so whenever it sees a rising edge, it will send one pulse. So this monoshot timer, what it does is, this generates a constant on time. Constant on time pulse. the moment it detects this rising edge, so whenever V naught is going below Vref, then this type of trigger signal will be generated by this monoshot timer. Sorry, by this edge detection circuit. Sorry. So once this edge detection circuit generates this trigger signal, which is named as FTR, then this monoshot timer generates an on time gate pulse. So it is generating this on time, and again this on time is predefined. So this constant on time is already predefined, and we can vary this as well. So this is a predefined value. Okay, so now V naught has charged and V naught has gone above. Now it is off, and here off time is not fixed, or like it is not predefined. Who is deciding the off time? The off time is decided by this comparator. So the gate pulse will remain off as long as V naught is above Vref. And again, the moment V naught comes below V reference, then again the on time is started. So important aspect is here T off is variable because on time is fixed. So in the case of fixed frequency, the duty ratio is variable, switching frequency is fixed. Whereas in the constant on time is fixed and off time is variable. And then when the off time or the off duration ends, so it ends once V0 goes below V. So what does it mean? Once the V naught again goes below V reference, then it means that it has to be charged. So the constant on time will charge it and then it will remain off. So the important question is this off time always fixed? Because V naught is discharging, and once it goes below V reference, then again on time is coming. So how is this variable off time? So depending upon the load, say if it is at light load, then the discharge rate will be slow. If the load is high, so then the discharge rate will be higher. So in that case, the off time will be variable. So it depends upon how my voltage curve is discharging, or how my voltage profile is changing. Say during low transient, V naught will see a dip, right? So in that case, the off time will be different. Whenever there is step down transient, then V naught will see an overshoot. So at that time, it has a different. So the off time will be variable depending upon the situation. Low transient, load means step up transient as well as step down transient, and depending upon the situation, it can vary. So T off can be zero sometimes, or T off can be maximum sometimes. So it depends upon the situation. And one more thing, I'm not going too fast, right? Like if you feel I'm going too fast, you can ask me to slow down so that I'll go at a slower pace. Is the pace fine to everyone? Don't hesitate if I'm going too fast or too slow, then you can let me know. Is the pace okay, or should I go a little bit slower?
It's fine, sir.
Okay. So one important aspect that I would like to highlight, fixed frequency modulation. So frequency is fixed, duty ratio is changed. So duty is variable. FSW is fixed. Now if you do COT modulation, constant on-time modulation, then we have on-time is fixed, T-on is fixed, T-off is variable. Okay. Now, there is also something called minimum of detection. So can anyone let me know why this is needed, or why minimum off is needed at all? Like why, what is its necessity in the first place?
Otherwise, the output voltage will become zero. It'll collapse.
Yes. So in this, sorry. So in this entire implementation, there is one flaw. Like, or I can say there is one assumption. The assumption is during the on time, we are assuming that the V naught is going above the V reference, right? Say, let me draw the waveform so that it will be more clear. So we have V not V reference and then trigger and then on time pulse. So I'm considering this as V reference. Sorry, this is my V reference. And say my V naught is something like this. Once it is crossing, and then again it is going something like this. So whenever this is touching, okay, so whenever this is touching, I will get a trigger pulse, right? So here there will be one trigger pulse, here there will be one trigger pulse, here there will be one trigger pulse, here there will be one trigger pulse. So if we name this, so this is my V naught, and this is my V reference, and this is my F trigger, and this is my Q pulse. So whenever there is trigger, there is some on time followed by off time. And here also we have on time followed by off time. And we have on time followed by off time, on time followed by off time. So till now, there is no issue as such. But let us assume there is a load transient here. So at this instant, let us assume there is a load transient. Step up, to be precise. Load, step up, transient, right? So now what happens is, basically V naught will see a dip, right? So let us say that V naught has seen a dip, okay? And then it is trying to charge back because of our constant on time. And then my on time pulse is fixed, right? On time is fixed. And then now it is off time. So from this instant, off time has started. So off time has started. But V naught is still less than V reference. So basically what is happening, V naught is below V reference. And because off time has started, now V naught will discharge, right? So this will never go up. So if it is not going up, then it will not come down. So FTR will never see a rising edge. So the off time will be the converter will forever be in off time, right? So what happens? And the V naught will discharge to zero. So converter will be converter will stay off duration, like off mode. V naught will collapse to zero. Is it clear for everyone how or why the system is collapsing? Like what is the need for minimum off time? Is this clear? Like if
Yes,
you
sir.
have still confusion, you can let me know. I'll explain, or maybe I'll explain. So whenever there is in steady state, or it is in steady state, there is no issue as such. On time is there, off time is there, on time is there, off time is there. But I have assumed, or it can be possible as well in the like any scenario. So I have assumed that there is load step up transient, and then V naught has come down below V reference, which has triggered this FTR. So on time has started. But at the end of off time also, V naught is still less than V reference because of the undershoot. Now off time has started. And who ends this off time? I have mentioned that off time ends once V naught goes below V reference. So only when V naught is going below V reference, then I will see a trigger pulse here because of the comparator. But not if it stays, if it is already staying there, then FTR remains zero because the comparator is zero. So I will never see this FTR. So now what happens is, because I will never see FTR, the converter will forever stay in the off mode. So when the converter is staying in off mode, V naught will discharge and V naught will collapse to zero and the converter will collapse. So now how to tackle this situation? So how are we tackling this situation? So every time the off time ends. At the end of off time, we will give minimum, sorry, at the end of minimum, like at the end of constant on time, we will give minimum off time. We will give minimum off time. Say I will give minimum off time till here, or I'll use a different color. So I will give minimum off time till here. And then I will check whether my V naught is less than V reference, because there can be a scenario where after the end of on time, my V naught can still be V reference. So I will give minimum of time. In that minimum of time, I will check whether my V naught is less than V reference or not. If it is less than V naught, if it is less than V reference, then I will forcefully generate the on time. So I will forcefully generate the F trigger. F trigger. So I will give another on pulse. So now what happens? This will try to increase, but it has still not crossed V reference. Then what I will do, I will again check. I'll use light color so it will be visible. So I'll give another minimum of time. And then again, I will check whether my V naught is less than V reference. If it is still less, then I'll give another forceful on time. So now it will cross. So once it has crossed, I will check whether it is uh, in the after minimum of time, I will check whether it is still less than V naught, so whether V naught is less than V reference or not. But it is above V reference, so I will not force anything because it is bound to come down. So now what happens is, now it will go in its normal dynamics, and then it hits here. So now that it is hitting here, so basically here I am generating force trigger. Here also I am generating force trigger. So these two are forced. They did not happen, but we have forced because of the situation the converter is in. We have to forcefully turn it on, else the converter will collapse. Now at this location, we are getting the pulse. So after the minimum of time, we are checking and we have checked that there is no need to forcefully turn it on. So we have left it like that. And now the on time has come to. So now if you see from our situation, here the switching time period is T. And here also T, or say T1. Here it is T1. Now here this is the switching time period, right? T2. So now what is the relation between T2 and T1? T2 is smaller than T1, right? Agree? Because here the off time is minimum off time. Is that clear? Hello?
No, sir. The T1 part. Can you just repeat once?
Okay. So whenever after the off time, constant, my bad. So once the constant on time has ended, there can be a situation where V naught is still less than V reference. So in that time, we will give minimum of time. And then after this off time, we will check whether the V naught is still less than V reference or not. Because if the V naught is still less than V reference, then there is no point in keeping the converter in off mode. So we have to forcefully turn on so that the V naught will go above V reference. So after this off time, we will check. I have checked that V naught is still less than V reference. Then what I have done, I have forcefully turned it on. So F trigger is not coming from my comparator. Instead, I am forcefully triggering it so that my on pulse will be generated. So now on pulse is generated, and again after this on pulse, I have given minimum of time, and again I have checked whether my V naught is less than V reference or not, and it is less than V reference. So I have to again generate the forceful on pulse. I have generated. After this on pulse, I have seen that the converter has, or the converter output voltage is above V reference. So I will no more forcefully generate this FTR. So I'll let the converter be in off time. Now that it is above V reference, it will discharge. So once it is discharging, then FTR will come. So now because of this FTR, my on pulse is generated. So when FTR is coming from the comparator, the off time is coming because V naught is discharging. So here it has a different off time. Whereas in this region where the off time is minimum, so this highlighted blue color region is minimum off time because the converter V naught is less than V reference. So there is no meaning to keep the converter in the off mode because it has to be turned on so that the V naught will rise above V reference. So in this particular duration, the off time is minimum. So the switching time period is T on plus T off minimum, whereas here it is T on plus T off. So this off time is more than this. So my T2 is smaller than T1 in this region. Is this clear?
Yes, sir. Now it's clear.
If you still have any confusion, you can ask so that I'll explain again.
Sir, with this method,
Yes.
we cannot make the duty cycle increase like because we are setting a minimum off time.
Yes.
So that means that we cannot increase the duty cycle beyond a certain range. Is that
Yes.
correct?
Yes.
Like
Yes.
because of
Yes. You
this?
are right. Yes.
Okay. Is that a
So
limitation? Like suppose if the voltage becomes high
yes.
before the minimum off time, then will
Yes.
that be a problem?
Yes, yes. Yes, that's a very good point. I'll just get to it. So whenever there is load step up transient, this issue will come. I will show by drawing the picture clearly. Thanks for not like raising that issue. So he has pointed out one limitation. I'll explain in few minutes. But one thing I wanted to tell is, so this FTR can either come from the comparator or because of our minimum off time detection, we are forcefully triggering this. So previously in our original architecture, it is coming from the comparator output, but there can be a situation where the converter can collapse. So sometimes we have to forcefully trigger this. So we are also taking the input from the comparator. If the comparator says that on time has to be generated, then it will be generated. But there can be a situation where the comparator output is zero, but still we have to forcefully turn it on. And in that case, the FTR dash is not coming from FTR, but because we are internally checking, from there we are getting this forceful trigger. And in that case, in that region, the time period will be minimum, or I can say the switching frequency will be maximum. So that's why the constant on time will need minimum off time. So that's why we have minimum off time detection. So that's why this constant on time will be needing minimum off time, and it is very much needed. Minimum off time. And one more thing, if you see, V reference is below V naught. So the reference is at the valley point. So that's why it is also called as valley control. If it is current based constant on time, then we'll have, if it is current based, then we'll call it valley current mode control. So valley current mode control can be of fixed frequency, variable frequency. So uh, in the variable frequency, constant on time is valley current mode control. And in fixed frequency also, we have peak current mode control as well as valley current mode control. So both are analogous. So now coming to his question, we have a load transient. So first I am considering step up. So this is spot control. Can be voltage mode or current mode, but like the working remains same. So there is a load transient. So this is my I naught, and it has gone from I naught 1 to I naught 2. So now we have current. So current is having constant on time, and then off time is coming from the loop. So now when there is a voltage transient, there will be on time, and then I am using minimum off time, and then on time, and then minimum off time, and then on time, and then minimum off time, and again on time, minimum off time, and then on time, and then now it need not be minimum off, so it will have some off time, and then again it will come down. Right. So now in this region, let us draw the gate pulse. Okay, let us draw the gate pulse using a different color. So my gate pulse will be here, it is almost fixed, although my uh, figure says otherwise. It is at steady state. Now what happens is the off time reduces. The pulses are very close by. Very close by, and here it is normal, and from here it is normal. So during this region, minimum off time is there. So because of this minimum off time, what happens is it cannot turn on continuously. So it can't turn on continuously. Can't be turned on continuously. So it will have some effect on the step up response. So during this region, the switching frequency will increase. However, this minimum off time will put a limit on the on time. So it cannot be turned on forever. Now let us come back to this is step up response. I'll also explain step down. Then you can ask questions if you have any. So now let us come back to step down response. So I'm considering step down. So we are going from I naught 2 to I naught 1. Now we'll see. So now we have constant on time. And once the load has come, it will turn off, right? So this is like an ideal situation, but in practical there can be transient. But I'm saying that this can be a possibility where it is turned off and then we can get optimal response. So now if we draw the gate pulses for this as well, as the off time is variable, the step down response will be really good for constant on time. So now we have on time, on time, on time, off time. So this is like a steady state. So if you see in this region, off time is maximum, or I can say FHW is minimum. So constant on time has perfect or better step down response, but not so better step up response because of the minimum of time. Whereas in the step down, it can turn on for continuous time without any limit. So it can be made much faster. So step down response will be superior compared to the step up response for quad control. Is this clear?
Yes, sir.
So others, if you have any doubts, then you can ask because we have discussed quad control in detail. Now off control, constant off time control, we can just quickly browse through and spend little time. If you have questions, you can ask me now. Okay. So I guess no questions. Then we'll move to voltage based constant off time. Okay, Arun says it is clear. Okay. So now voltage based constant off time control. So it is analogous. Like previously, I have said that is valley mode control. So this is peak mode control or peak control. Analogous to peak control. So now if you see the sign has changed. Whenever V naught is crossing V reference, then it will raise a trigger. Now monoshot timer, what it does is it always gives an on time pulse, but we need off time pulse, right? Because it is constant off time. So that's why we have put an inverter, because monoshot timer always gives fixed on time pulse. So now the output becomes fixed off time pulse. So that's why the inverter is there. But the overall logic is the same. So now if you consider a similar type of figure, maybe I'll use this for better understanding. Similar to constant on time, here also there will be issue. Or better, I should draw again rather than modifying. That will take less time. Okay. So here V reference is at the peak. And V naught is below. So whenever V naught is trying to go above V reference, then the trigger will be circuit, like given. So if we draw this one, so whenever it is hitting, then we have constant off time followed by on time. And then who ends the on time? Once it is hitting, then the on time is ended. So once on time is ended, there will be fixed off time, and then there will be on time. And then once it hits, the on time will be stopped. So here the off time is fixed. So off time is fixed. And on time ends once V naught goes above V reference. So now the same question can be applicable here. What if the V naught is already above V reference before the on time starts? So what I'm trying to say is, say there is a load step down transient. So there is an overshoot. Okay. So now because it has gone above, there is a off time and the on time has started. So at the end of the off time, once the on time has started, V naught is above V reference. So when will the on time ends? The on time will end when V naught is crossing V reference. So it is not just above when V naught is crossing V reference and going above. When V naught is crossing V reference while increasing, but it is already above V reference. So now what happens is the on time will not end and the V naught will keep on increasing. So in this case, it is opposite. There off time is not ending. Here on time is not ending. So on time doesn't end. So now what happens? V naught will increase and the devices can get damaged. So there V naught is collapsing to zero. Here V naught will keep on increasing and the devices will get collapsed or damaged. So now what we are doing, instead of giving on time, we will again check for minimum on time. And we will see, okay, V naught is above V reference. We need to turn off. So now we are turning off for fixed off time. And then it tries to count down. And then the on time will start. And then we'll check that, Okay, for minimum on time we have to turn on because it is still above, and then the off time starts. So now at the end of this off time, say it has come down. It has come down. Now we'll turn on, and then once it crosses in here, the off time continues. The on time continues, and then from here again it remains the same. So there it is slightly different. Here it is slightly different. If you see again here, the time period T1 is higher, and here T2 is small. So again, T2 is smaller than T1. So when the on time is minimum, the switching frequency will be maximum or the time period will be minimum. Is this part clear?
Yes.
Similarly, I will take this figure. I will paste it here. Okay. So now we are doing constant off-time control, which is also sometimes called as COFT control. So constant off-time control, COFT control. So in the case of stepper, what can happen? My on time can be different, right? So we don't have this issue. So the response will change. How will the response look like? The response will look like something like this. So now what is happening? This entire time is on, then off, then on, off, then on, on. So here we have maximum on time. Maximum on time, which means our switching frequency is, or instead of using switching frequency, our switching time period is maximum. Now, if we come back to step down transient, here it will suffer because there is minimum off time. So it cannot be turned on like that. So now what happens is it has this minimum off time, right? So it has this minimum on time, right? So constant off time, there is less than a minute. So if this meeting ends, kindly join that. Minimum on, constant off, minimum on, constant off, minimum on, constant off, minimum on, constant off, minimum on, constant off. If this meeting ends, kindly join that. So it is coming something like this. So if we draw the gate pulse, will be like off, then small on, off, small on, off, then minimum on, off, minimum on, or on. So in this time or in this uh, duration, minimum on time. Minimum on time. So here again the switching frequency is maximum. So here FSW will increase. So in the case of constant on time, step up transient was suffering and step down transient was superior because it has variable off time. Whereas in the case of constant off time, it has superior step up transient, whereas the step down transient is suffering because of the minimum on time. So that is peak. This is valley control. The constant on time is valley control. And then this is peak control. And there you will need constant on time, right? So minimum off time. Here it is constant off time. So it will needs minimum on time. So both are like opposite to each other. And that is the key difference. And because of this kind of response, variable frequency is very much important because it will significantly improve the response. Whereas in the fixed frequency, the frequency is fixed. So it has some duty ratio limitation in either the step up or the step down. Whereas in the case of a variable frequency, the frequency is adjusted accordingly. So the response will be much, much superior. Is this clear?
Yes, sir.
So now if we put both the limitations on peak as well as valley, then we'll get hysteresis. So it is voltage based hysteresis control. So here what happens is we have uh, upper limit as well as lower limit. So there will be two comparators. So once V naught is going above VH, it will turn off. Once it is going below VL, it will turn on. So here both on time as well as off time are variable. So both T on and T off are variable, but it is slightly difficult because it needs two fast comparators. And also protection regarding that, because if V naught is not within this band, then we have to protect it. Like if V naught is above uh, VH at some condition and then it is on, then we have to forcefully turn off. So additional protection circuit is also needed because it will have the issues of both constant on time as well as off time. So it might need to have minimum on time as well as minimum off time. Also, we can calculate the on time because we know the height and we know the slope, so you can calculate the on time and you can also calculate the off time. So how can we calculate? We know that VH minus VL is nothing but MV1 into TM. Similarly, VH minus VL is MV2 into TO. So from this, I can calculate my switching time period as T on plus T off, which is VH minus VL, VH minus VL into 1 by MV1 plus 1 by MV2, right? So here, switching time period, both on and off are variable depending upon the hysteresis band. So I can choose this band, which is denoted by delta VH. Now the band can be made little bit more, then time duration will be more. If the band is small, then the time duration will be lesser because it is directly proportional to this VH minus VL. So in the case of hysteresis, this is how we calculate switching time period. Is this clear?
Yes, sir.
So till now we have discussed about constant on time, constant off time, as well as the hysteresis band. Now, because it has a hysteresis band, so instead of two comparators, one hysteretic comparator can also be used, which is an alternate solution. And one such circuit is the Schmidt trigger. So that's why it is important that we need to study. So this is one of the positive feedback circuit. Usually op amp is connected in negative feedback because that is stable. but this is one of the circuits where it is connected in positive feedback. As you can see, the feedback from V0 is connected to the positive terminal. You know that the current entering the input terminal of the op-amp is 0. So now I can get Vp. Vp is nothing but R1 by R1 plus R2 into V0, right? Or you can say V0 can be either VH or VL. So V0, Vp. And then Vn is what? Vn is Vin. So because it is positive feedback, if Vp is slightly more than Vn, output will be maximum, which is V plus. If Vp is less than Vn, then it will become V minus. So basically, my V naught is A into VH is like the positive voltage into R1 by R1 plus R2 minus Vn. So now what happens? From this condition, if my VH into R1 by R1 plus R2 is greater than Vn, then my V naught will become what? Vp is higher, right? So V naught will become V plus. If my VH into R1 by R1 plus R2 is less than V, then my V naught will become V minus. So it will toggle between V plus and V minus depending upon my input and then this expression value. So whenever V in is crossing this, the output will toggle between V plus and V minus. And now the hysteresis band can be set by choosing this resistor. So these resistors can be chosen accordingly so that my hysteresis band can be adjusted. Is this clear?
Yes, sir.
So I think in assignment also similar kind of question was asked. I think V plus and V minus values are given, resistor values are given, and say this. If you calculate this, we'll get some 5 volt, and then in the question they are toggling V in, right? V in is changing from I think minus 10 to 10, so they have this type of circuit where V in is toggling between minus 10 to 10. Okay, so maybe I should bring this down. Okay, so this is my V in. Say the black color waveform is my V in, and then so now I have calculated this, so I am getting +5 and -5. So this is my +5. Did I use red color? This is my +5 volt, and this is +10 volt, and this is my -5 volt, and this is -10 volt. So what does my calculation says? If my V in is greater than this -5 volt, then V naught will be V minus. If my V in is less than 5 volt, then V naught will be positive. So now in this region, say this is 5 volt, right? So once my V in is crossing 5 volt, then what happens? So if V in is less than 5 volt, if V in is less than 5 volt, then what happens? If V in is less than 5 volt, then it is becoming V naught is V plus. But if my V in is more than 5 volt, then again it is becoming negative. So once this V naught crosses this 5 volt, it is becoming negative. So the output will be negative, right? And now until here, it is above the 5 volt. So it stays negative. Now coming back here. Now coming back here, my V in is less than what? This Now it becomes -5, right? Because in this region it is -5. So my Vin is less than -5. So my output will stay positive. So after this, it stays positive until which region? Until it cross +5. So the same will be reflected here. So is this clear how we are solving? So we have to go with this condition where Vin is standing, and based on the Vin, we'll see whether V naught is toggling between V plus or V minus. And from this, we can get the waveform. So first you need to draw the waveform and see what are the limits. So from here, say assuming this is 5 volt, I got the limit +5 as well as -5. And now I'm checking my Vn is above this or below that. Is that clear?
Yes, sir.
If you have any questions, you can ask, else we'll start solving few problems.
Sir, in the theory part, there was
Yes.
one part that was given that during peak CMC control method, like duty cycle, if it is more than 0.5, then it will
Mhm.
become a current loop is unstable. And
Yes.
similarly, the other way around for this. So, but the why of that was not explained, sir. So just
Okay, I think it is not explained. I have to check whether sir has derived that or not. But in another course of his, sir has explained. Like it all comes from the stability aspect. So what happens is we have peak current mode control, something like this, right? And say peak reference is fixed. Now what we are doing is we are perturbing it, say up or below. So now this is the perturbation and it goes here and then it comes here. So now we have to see how this is getting changed. So for any perturbation in this IL tilde, how my this waveform is changing. So we have to check like if there is any perturbation in the like duty ratio here. Basically, duty ratio is getting perturbed. Now we need to check whether that is trying to improve or whether that is trying to degrade. So we have to. So now this is say IL1. Now it has decreased, right? So now it has become IL1 minus IL1 tilde. Now we have to calculate this point. And basically, if a system is stable, the perturbation that we have given over here, so the perturbation that we have given over here, that should decay, right? So over the period of time, the perturbation should decay. If it doesn't decay, then the perturbation is basically keeping on increasing and then the system is unstable. So in the case of peak current mode control, what we will be getting is if my duty ratio is less than 0.5, basically sir is saying that it is stable. Whereas if the duty ratio is greater than 0.5, then like it is coming unstable. So in the case of peak current mode control, it is stable for duty ratio less than 0.5. In the case of valley current mode control, the duty ratio is coming greater than 0.5. For this, it is stable, and for this it is stable. Whereas in the case of, again, this is in fixed frequency modulation. Whereas in the case of variable frequency, there is no such stability. It is stable for entire duty ratio for both pod as well as COFT. In either of the cases, duty ratio can be anything, and we have also seen that. So I can give you one lecture where sir has derived this in another course. Maybe it was not part of this course, and that's why sir has not covered. But basically, it is coming from the perturbation. So whenever we are perturbing this, we'll have to calculate this new expression in terms of this old expression, and we'll have to check whether the perturbation is decaying or actually it is derived in lecture 23. So Arun is saying it is derived in lecture 23. So from there you can see whether the perturbation is coming, like it is diminishing or whether it is increasing. So based on that, we can get the stability aspect. So you kindly go through lecture 23 once and then we'll be able to understand. If you do not understand, then you can ask me, I'll explain.
Sure, thank you.
Okay, if you have no more queries, then we can start solving. So kindly go through this question and then we can discuss. So here I am asking to derive the inductor current ripple expression of a buck converter when it is being controlled under pulse width modulation, constant on time as well as constant off time. In which of these cases does the inductor current ripple increases with the input voltage? So what is the ripple expression of a buck converter? Can anyone tell me? Delta IL.
V in minus V naught by L into T on.
Okay. So let us start with A part. So we have to see in PWM what is constant in constant on time, what is constant in constant off time, what is constant. So then we can see whether it is increasing or not. So delta L is V in minus V0 into T on by L. So in PWM, what is constant?
TSW.
TSW. So we have to write everything in terms of TSW because T1 is not constant. We cannot say whether delta L is increasing with Vn or not because T1 is also dependent, right? So we have to write in terms of those variables from where we can conclude something. So V naught is constant. So I will write everything in terms of V naught and V in. So V in minus V naught into dTs by L. And duty ratio is what?
V naught by V in.
V naught by V in. So V in minus V naught into V naught by V in into time period by L. So if I take V in common, I will get V naught into 1 minus V naught by V in into Ts by L. Is this correct? Is this correct or am I making any mistake?
It's correct.
So now tell me whether if V in increases, ripple increases or it decreases.
Ripple increases when V in
Ripple
increases.
increases, yes. So if my V in increases, then it is implying that my delta IL also increases. So in the case of PWM, if the input voltage increasing, the inductor current ripple is increasing. Now let us shift to constant off time and then see whether it is the same or not. So in the case of constant on time, what will be my delta IL? So how to write delta IL?
V naught into T off by L.
In constant on time.
Oh,
This is on
Vn
time.
minus V naught into T on by L.
Yes. So we can directly write V in minus V naught into T on by L, where V naught is constant, T on is constant, as well as L is also constant. So now here you tell me whether my ripple increases if V in increases or it decreases.
Increases
Vn
when
increases.
V naught increases.
Yes. So here also, if my V in increases, then my delta L increases. Now in the case of constant off time, what will be the expression? Delta L.
V naught into T off by L.
Very good. V naught into T off by L. So here, what happens if V in increases?
No
Insensitive
impact.
to V.
Yes. So the ripple is independent of mean. So in this case, we'll get that delta L is independent. Delta L is independent of V. So in this case, so what is the answer then? So what is the answer? ABC in the ABC. Naveen is saying COFT
A and B.
control. What about others? So in which cases is the inductor ripple current increasing with input voltage? PWM.
A and B.
So yes, A and B. So it is increasing in both A and B. Whereas in the case of constant off time, it is independent of the input voltage. So is this question clear for everyone?
Yes, sir.
Yes.
Now let us let us go to another question. So in this question, let me read out. Consider a boost converter operating under hysteretic current mode control. So the difference between current mode control as well as hysteresis voltage mode control is here the voltage is in between two limits VH and VL, upper and lower limit. Whereas in the case of current, this will be the current waveform. Current will be in between upper current limit as well as lower current limit. So that's the only difference. So in the case of boost converter, they're saying it is operating under hysteretic current mode control with an inductor current ripple of delta IH, which means I maximum minus I minimum is equals to delta IH, the ripple. So calculate the switching frequency of the converter as a function of input voltage, output voltage, inductance, and inductor current ripple. So let me draw the so we have upper limit and then we have lower limit. I am calling this as I max. And I am calling this I minimum. So the difference between them is called delta IH, which is again given. So now the inductor current is changing like this. So this is my T out. And this is my T out. So the question is saying, or like what we are being asked is how to determine the switching frequency of this converter as a function of input voltage, output voltage, inductance, and the inductor current rate. So how can we calculate anyone? How to proceed?
ESW equal to T on plus T off. Then T on equal to delta IH by M1. T
Yes.
off equal to delta IH by M2.
Yes, very good. So we know that this is slope is M1, this slope is M2. We can calculate T on and T off. So T on is nothing but delta IH by M1, and T off is nothing but delta IH by M2. So now you can get switching frequency is nothing but delta IH into 1 by M1 plus 1 by M2. So what is M1 and what is M2 in the case of boost converter?
M1 is V in by L.
So M1 is basically V in by L, and the other one slope.
V out
So
by
slope
L.
is a magnitude.
V out by L.
V out or what exactly is it?
V out minus V in by L.
Yes, V out minus V in by L because it's a slope. So it is L by V out minus V in. The voltage across the inductor is V in minus V0, but the slope we are considering positive because this is already considered as a negative slope. So because it is we are calculating the time, it is slope positive value into off time, that is delta H. So we are considering the positive value. So now if you take the inductance outside, you will get delta IH into V naught by V naught minus V in into V in, right? Clear? Is this correct or have I made any mistake?
L on the numerator.
Oh, sorry, L is there. Clear?
Yes, sir.
Now what will be the switching frequency?
1 by of this expression.
1 by this expression, right? So FSW
Yes.
V naught minus V in into V in by V naught L into delta LH. So this is how it is calculated. So based on the requirement, so if it is a buck converter, M1 and M2 will change. If it's a buck boost converter, M1 and M2 will change. But the process remains same. Basically, we are calculating different slopes for the given converter. The expression remains same for both buck boost for all the converters because it is dependent on delta H, M1 and M2, which are generic. Now, depending upon the converter, M1 and M2 values will change. So depending upon that, our switching frequency will change. So if they're asking in terms of duty ratio, then you have to substitute the duty ratio of that particular converter in this, and then accordingly you can calculate. So that makes sense, right? Is that clear?
Yes.
Yes. Okay. So now let us, if you do you have any queries? If you have any queries, you can ask, else we'll move to another question.
Clear, sir.
No queries? Okay. So just give this question a read. I'll give you some time. Then we can start solving. Clear or any doubts? If the question is clear, then maybe you can start solving. I'll give you some time. If it is not clear, then you can ask. Okay, have you understood the question?
Yes.
So just give it a try. I'll give you 2 minutes and then you can, then I'll start solving. So are you solving? How many of you have solved part A?
Sir, is it 506 kilohertz?
506 kilowatts. Okay, let me check. So others are getting the same answer. So let us start solving. So we know the delta IL expression is V in minus V0 into V0 to dTs by L, right? And then they're asking the time period. So I can bring this. Ts is nothing but delta IL into L by V in minus V0 and duty ratio is V0 by V. So everyone is getting this. Time period is nothing but delta IL is 10 amperes into inductance is 150 nano by V in minus V0 is 15.2 into V0 is 0.8 into V in is 16. So has anyone calculated the value? How much are you getting? 150 nano, let me calculate. 10 into 150 nano by 15.2 into 0 0.8, everything into 16. So if we multiply by 10 to the power 6, it is coming to be 1.973 microsecond. So I got switching time period as 1.973 microsecond. So from this, we can calculate the switching frequency. So is the inverse of this. So it is coming around 506.6 kilohertz. Yeah, whoever has said that it is correct, it is coming 506. Very good. So now in the other part, has anyone solved the other part? What will be the switching frequency of the converter if it is operating under constant on time and the on time is given as 100 nanosecond? Has anyone solved this? Hello? How to proceed for this question? So what is on time in terms of duty ratio and switching time period? Anyone? On time in terms of duty ratio as well as time period.
D into TS.
Yes. So my T on is nothing but duty ratio into time period. So what is my on time? 100 nanosecond. And what is my duty ratio? 0.8 by 16, right? Into switching time period T. So now what is my time period T? So this get cancelled 20 times. 2 microsecond, right? Or am I wrong? What is the time period?
2000 nanosecond. So 2 microsecond.
2 microsecond. So now it is also saying 2 microsecond. Sorry. So it is 2 microsecond. So what is the switching frequency there? So there is less than a minute. If this meeting ends, kindly join back. So what is the switching frequency?
500 kilohertz.
500 kilohertz. So is everyone able to understand how we are getting this? So in the first question, we have given it is PWM and we have given the ripple requirements. In the second case, we have given the on time as 100 nanosecond. And based on that, we are asking what is the switching frequency. And maybe there could be a mistake that for this on time, this ripple might not be possible. So what I should have done is, if delta L is 10 ampere. Yeah. So this might be a mistake because I have given on time. Maybe for that on time, delta L may not be 10 ampere. So delta L is given only for the first part. So in the second part, they have directly given on time. So we are getting this switching frequency. So this may be a mistake. So I have rectified it. Okay. So in the third part, I have said that the converter is operating under constant off-time current mode control with a switching frequency of 700 kilohertz. Then what will be the off-time? So how to solve this third part? How to solve this, anyone? Off-time is given. Sorry, off-time is asked and switching frequency is given.
So delta L equals to V naught into T off by L.
Yes, yes. One mistake, like delta L is only given for the first part, not for the other part. So that was my mistake. So I have rectified because it is not needed for the second part. If on time is given, then delta L is not needed and it may not be 10 amperes also. So it was only for first part. So in the third part, they have not given delta L, they have given V in, V naught L as well as switching frequency and they're asking off time. For the third part, they have given switching frequency. They're asking off time, given V in, V naught as well as inductance L. So this is the hint. Similar to part B, we have to do for part C as well. So now you get any idea how to do?
T off equals to TSW by D. So
1 minus D into T, right?
1 minus D into, yeah, 1 minus D into.
So T off is nothing but 1 minus D into T, and they have given us switching frequency. So it is 1 minus D by switching frequency. So now what is D? 0.8 by how much? 12 or
16.
15? 16. So 0.8 by 16 by 700 kilohertz. So now calculate off time in microsecond. So T off. So you also calculate, I'll also calculate. We'll cross check the answer. So Navin is saying 1.35 microsecond. Let us wait for others and let us cross check if we are getting the same answer. So others, let me know whether you are also getting the same answer.
Yes, sir. 1.357 microsecond.
1.35 microsecond. Okay, very good. So off time is 1.35 microsecond. So in this way, we can twist the question around and then we can ask. So now if I ask in which of these cases the ripple is independent of input voltage, in which case it will be independent?
The constant off time.
Constant
C.
off time, yes. So because we have already checked in this first question where it is independent of the input voltage in the case of constant off. So is this clear until this point, the theory plus the questions? Then we can move to some more interesting topics. Yes. Okay. So if you have any queries, you can stop me, else we'll move to another topic, which is light load modulation techniques. Okay. So, so the issue with the converter at light load is the losses will increase if we operate in CCM. So losses will increase if we operate in CCM. Because in the case of continuous conduction mode, the RMS current is dependent on both average as well as ripple. So we cannot afford so many losses in the converter at light load because it is powering less power. And if the losses are more, the efficiency will come down. What is the effect of this? If we operate in CCM, the efficiency will go down. Now what we are doing is we are operating in DCM. So this is DCM operation where the inductor current will not be let to go below zero. So this is DCM operation. In this case, what we'll do is once the inductor is turned off, we'll let the inductor touch zero, and once it touches zero, then we'll let it be like that until again it starts. So now this is fixed frequency operation. So TSW is fixed, and then only the duty ratio is changed, and then once it hits zero, we'll keep in this zero region. So this is fixed frequency DCM operation. So again, the frequency is fixed. So it is fixed frequency DCM operation. So is this part clear?
Yes, sir.
Now coming to another part, here we have constant on-time based DCM. So the on-time is fixed and the off-time is variable. So this entire time is off-time, this is on-time. So in this off-time, we have certain region where inductor current is positive, and then there is another region where the inductor current is zero. So here on-time is fixed and the off-time is variable, and the switching period is done accordingly. Here we have fixed frequency. So here it is constant on-time. Constant on-time based DCM operation. So there are different types of light load modulation techniques, and each of them have their uh, pros and cons. Once I complete all these things, then I'll explain what are the pros and what are the cons. So this is adaptive on-time based DCM operation. So this is adaptive on-time. On-time current mode control. You can say for DCM operation. DCM operation is also go. So why adaptive on-time? So basically here we are fixing the I peak. So I peak is fixed. So once I peak is fixed, on-time is adjusted accordingly. Because we have seen in constant on-time control, the inductor ripple increases with the input voltage. And what is the main disadvantage at the DCM or like at light load operation is we want to limit the ripple also, right? If the ripple increases, then the RMS current increases, the losses increases. So we don't want the ripple to increase as a function of input voltage. So one thing is we can use constant off time, or here what we are doing is we are fixing the peak. So my peak is fixed, my on time is adjusted accordingly. So that's why it is called adaptive on time. And who decides my off time? My off time is coming from the outer loop where there will be a comparator of voltage. And again, it is DCM operation. So here we are having the advantage of variable frequency as well as we are having the advantage of fixed I peak. So maybe it would be good if I also point out the like flaws or what are the like disadvantages. Here in this case, the switching frequency is fixed, right? FSW is fixed. So switching losses can be high because if I'm operating the converter at high frequency, switching losses are still high, right? At light load, the switching losses are still high. Say I'm operating the switching like converter at 500 kilohertz, and now it is supplying 0.1 amperes. It is not required for me to operate at 500 kilohertz because the switching losses will be so high, the efficiency will be very poor. Now, in this case, what is happening? It is constant on time. The switching frequency is variable. But what is the disadvantage? The ripple is dependent on input voltage. Here, ripple is still dependent on Vn. If my Vn is changes, my ripple will also change, and then that can still affect my efficiency. So here I have advantage. One is the switching frequency is adapted. So at light load, it uh, depends upon the load current. So sir has derived in his one of the lecture, FSW is dependent on I naught. So if my I naught is going down, switching frequency will go down. So the switching losses will go down. Also, my peak is fixed and accordingly my on time is adjusted. So I have advantages in terms of ripple as well as efficiency. So efficiency is better. Efficiency is good. Also, ripple is fixed. So it has few advantages. And now coming to pulse skipping modulation. PSM stands for pulse skipping modulation. So in this case, what happens is instead of operating at higher frequency with the same gate pulse in each and every cycle, what we will do is we will fix the duty ratio. So the duty ratio is fixed, and in each and every cycle, we will check whether the output voltage is below the B reference or not. If it is below the B reference, then only we will charge. Else, we will skip the pulse. So it has two set of So this is charge pulse. So it has two set of pulses. This is skip pulse. And again, this is charge pulse. So it is basically fixed duty ratio. So duty ratio is not fixed. I mean, duty ratio is not variable. Also, the time period is also not variable. So here, D is fixed. When I'm talking about D, I think I should not say D. I should say the gate pulse, this T on is fixed. So T on is basically fixed. The gate on pulse is fixed. Also. So T on is fixed here. And also the time period T is fixed. So what is varying here? Whether the charge pulse should go or not, that is varying. So if you see in this below case, the effective time period is this entire time period, right? But one charge pulse time period and on time is fixed. But the effective time period can vary depending upon whether we are charging or whether we are skipping. So when I am saying T, this T and this T on both are for the charge pulse. Okay. So the charge pulse on time as well as the switching time period is fixed. Now depending upon my output voltage, I will either I will charge the output or I will discharge. I mean, I'll not charge the output. So in that time, the output is getting discharged. So here, what is the disadvantage is here the time period, effective time period, T effective is always some integral multiple of time period. It is not any other value, right? So my effective time period is say 1T or 2T or 3T or 4T. But what if I need like according to my load current, it does not always mean that my effective time period should be 2T. Say T effective, I need 5T or say 2.5T. Then how can I get 2.5T? Because my T effective is K into T, right? So in this case, how are we getting 2.5T? Anyone?
By skipping one pulse.
Yes. So basically what happens is effectively either you can get T, 2T, 3T, 4T, 5T, right? But you cannot get 2.5T. So what happens is you will not get 2.5T directly from here. But basically what happens is say it will have 2T time period, say for 10 cycles, and then maybe 3T for 10 cycles. So effectively what happens is it has a 2.5T, but 2.5T is not a steady state value. It can toggle between two set of time periods. So there can be oscillations because of this, because 2.5 cannot be achieved from here, right? It has to be a multiple of time period. So it might so happen that for certain cycles, it has certain time period, and after some time, it has a different set of time period. So that effectively, in an average sense, it is having 2.5T. But because of this, it can have slight oscillations because for certain time, it has a different time period. For the rest of the time, it has different time period. So is this clear how this has certain issue in terms of effective time period?
Yes, sir.
Hello.
Yes, sir, it's clear.
Okay. So we have discussed about four types of one is PWM operation with DCM, another one is constant on time with DCM, another one is adaptive on time with DCM, the fourth one is the pulse skipping modulation. So depending upon our application, we have to choose one of these. It does not mean that always I will go for adaptive on time. Maybe sometime depending upon our resources and requirement, we might have to go for one of these. So that's why we have different type of choices, and whatever fits our application, according to that we have to go. So if you don't have any queries, then we'll go to our last question. So give it a read and then we will see how to solve. So I'll give you 1 to 2 minutes. You give it a read and give it a try. Then I will start solving the problem. So the question is, consider a buck converter operating under adaptive on-time control with the following specifications and calculate the inductor current ripple if the on-time is 120 nanosecond. And what will be the switching frequency at CRM operation? So what will be the inductor current ripple? How to calculate?
Sir, 7.
Uh-huh.
7 answer.
That I have to check. I have to check.
Okay.
So what is the answer that others are getting? Okay, let me solve and check. So delta N is nothing but V in minus V0 into T on by L. So V in minus V0 is how much? 10.5 into T on is 120 nanosecond by inductance is 180 nanometer. So it is 2 by 3 into 10.5. So 10.5 into 120 by 180. Yeah, it is 7. You are right. So delta L is 7 amperes. So if it is operating under adaptive on time, can you tell me what is the I peak value? I peak?
7, sir.
7 amperes. Yeah, very good. So at CRM, what will be the switching frequency? So how to solve part B? So anyone, how to solve part B? Have you understood the question? Part B. What will be the switching frequency at CRM?
So
So what is
delta
CRM?
IL minus I peak by 2 equals to 0. Like that we can.
IL?
IL delta IL minus I average by 2.
Yes. So basically at CRM, we know that it is just,
Sorry, I average minus delta IL by 2 equals to 0.
yes, is equals to 0. But basically we are asking switching frequency and we know the on time. On time is fixed and then we know V in and V0. So I can use this equation T on is basically D into T where duty ratio is V0 which is 1.5 by 12 into time period T is equals to 100 nanosecond, right? You are right. When we are asking the critical resistance, then we'll use this IL average is nothing but delta IL by 2. So from this IL average, which is V naught by RC, then I can get RC because RC is unknown. I cannot calculate the time period based on this expression. So first I have to calculate the time period. Given the on time is 120 nanosecond. Sorry, not 100, 120. Hold on. So this is 120 nanosecond. So I have asked the switching time period, right, or switching frequency. So now switching frequency is nothing but 1.5 by 1440 nanoseconds. So now what is the switching frequency? So Naveen is saying 1 megahertz. Let us check whether we are getting the same or not. So what is the answer that everyone else is getting? FSW? Anyone? Rahul?
Doing some 1 second.
Sorry? I am getting 1.04 megahertz. So can anyone confirm if you are also getting the same expression? I mean, same value. 1.04, yeah. Okay, so now if I ask what is the value of RC critical resistance? So what is the critical resistance RC value?
V0 by RC equal to delta L by 2.
Yes, so delta L by 2 is 3.5, V naught is 1.5. So RC is 1.5 by 3.5, which is 15 by 35 and 3 by 7. So RC is 3 by 7 ohms. Clear? Everyone, how we have calculated RC? So basically we have calculated from this expression. Is this clear for everyone?
Sir, that last part, delta IL by 2, can you just explain once? I didn't understand that part.
Okay, so at CRM operation, we know that like this is delta here. And then once the triangle, like in the triangle property, we know like if we have a triangle, then the midpoint or the average in terms of inductor current is like half of the height, right? It passes through half of the height. So we know that IL average is nothing but delta IL by 2. And IL average is what? V naught by R. So at CRM operation, basically this is all CRM operation. So at critical conduction mode, delta IL by 2 is nothing but the average inductor current, which is V naught by R because it is buck conductor. So this is what I think we have discussed last week, CRM operation. So when this is the inductor current, the average current passes through the midpoint of the height, which is delta L by 2, which is the average inductor current. So from here, we can get the critical resistance. So at this critical resistance, it is just CRM operation. Is that clear?
Yes, sir. Clear now. Thank you.
So let me quickly summarize. In today's session, which is week 4, we have discussed about variable frequency control methods. We have started with the voltage-based constant on-time control, which is also called as COFT control. So we have understood the operation and how it is working and how the gate pulses are generated. And then we have realized that it also needs minimum off time, else the V naught will collapse. And we have understood the working of minimum off time and how the minimum off time will help us to not collapse the system. And then we have seen that sometimes it forcefully triggers the gate pulses with constant on time, and in that case there will be minimum off time. And then we have also seen that CORD control will suffer from the step up response, whereas it has superior step down response. Then we have moved to constant off time control, also it's a peak control, whereas constant on time is valley control. And we have seen that the working is just the opposite of the constant on time control. And in constant on time control, we needed minimum off time, and here we need minimum on time. And then we have seen how the minimum on time works and why it is needed. And we have seen that without that, the V naught will increase and the devices can get damaged. So this type of minimum off time and minimum on time protection is needed so that the converter will come back to the steady state. And then we have also seen that constant off time control has superior step up transient response, and it suffers in step down response, which is just the exact opposite of constant on time control. Then we have also discussed about the voltage based hysteresis control. Again, current based hysteresis control, we have current ripple here and then limits on upper and lower end. And we have also seen how using this diagram we can get the switching time period based on the slopes as well as the delta VH. And also we have seen hysteretic comparator can be used for the implementation of the same. So we have moved to the hysteretic comparator. Kind of one example is the Schmidt trigger, where it has positive feedback, and we have seen the input and output relation and how we can get the output waveform if the input is varied. So I have taken one similar example of what was given in the assignment. So based on this, I have drawn the expression. I mean, I have drawn the waveform because I have considered this to be 5 volt, and this is varying from plus 10 and minus 10 volt. So depending upon this condition, we can get whether my input is plus V or minus V. And then we have solved one problem where I have given buck converter, and I have asked in all these modulation techniques where the inductor current ripple increases with the input voltage. For A and B, it increases. For C, it is independent of the input voltage. And in the other question, I have considered a boost converter with hysteresis current mode control, and I have asked the switching frequency expression in terms of input voltage, output voltage, and inductance. So we have gotten the expression in terms of slopes, and then we have calculated the switching frequency expression. And in the case of buck converter, I have given another question based on constant on time, constant off time, and PWM. In each of these cases, I have asked the switching frequency calculation. In the third case, I have given switching frequency and I have asked what should be the constant off time. So based on the ripple and duty ratio on time off time expressions, we have solved this problem. Then we have moved on to light load modulation techniques, where we have discussed the necessity for light load modulation techniques and different type of modulation techniques like PWM based DCM operation, constant on time based DCM operation, adaptive on time based DCM operation, as well as pulse skipping modulation. Each of them have pros and cons, and we have seen what are the key differences between this. And then we have solved one question based on the buck converter based adaptive on time control, how the inductor current ripple can be calculated if the on time is given, and also at CRM operation, what will be the switching frequency and what will be the critical resistance. And we also got one question, which is the stability of peak current mode control, why it is stable for duty ratio less than 0.4. Due to lack of time, I could not explain this part. However, I think sir has explained this in one of the lectures, and someone has pointed, I think 22 or 23 lecture. So you please go through that. I think sir has explained clearly. If you still have doubts, then we can get this clarified in the upcoming video. So if you have any more queries, then we can discuss. I'll end this session here. So not just this stability anywhere, what we do is we give a perturbation, and then we'll see whether the system in the system or a period of time the perturbation is decaying or not. If the perturbation is increasing, it means it is unstable. If the perturbation is decaying, it means it is stable. So based on this, sir has derived the expression. So in peak current mode control, we'll get duty ratio less than 0.5, and valley current mode control, we'll get duty ratio greater than 0.5. So if If things are clear, then I can end this session. Else, if you have any queries, you can ask. So, I will be saying thank you. Thank you. So, any feedback that you want to give regarding these sessions, like what can be improved, so that I know that you are giving in Excel sheet, but if you can directly tell me, then I'll consider it positively, and then I can change it accordingly in the upcoming weeks, so that you'll also get benefited and I'll also get it. So, if you feel anything has to be improved, like then you can say it freely. No need to explain. You can mention in the chat as well, or you can unmute yourself and you can tell me as well.
All good, sir. Thank you.
Okay, thank you. Okay, like if you are typing in the chat box, if you have any suggestions, then you can type. Else, I think we can end this session here. And I wish you all the best for your assignment 4. And we'll meet again with week 5 problem solving session next Monday. I think next Monday it's about small signal modeling and state space modeling. I have to check what it is about. We'll meet again next week. Well, thank you everyone for joining. It's a nice session. Thank you, Naveen. Thank you, Arun. Thank you, Rahul. And thank you, Balaji. So,
Thank you, sir.
yeah. So I'll
Thank you,
end
sir.
this session here. Good night, and I wish you all the best.